Hello everyone, so this is problem number 61 from the chapter Rotational Mechanics from book H.C. Verma. Here it is saying that suppose the particle of the previous problem has a mass m and a speed v before the collision and it stick to the rod after the collision. So initially this is having a mass m, velocity v, and this rod was at rest, and after the collision this rod and the mass m, they both stick to each other. And suppose this is the center of the rod, this is the center of mass of the system, which is at a distance of x. So what is going to happen, that the center of mass is going to gain some speed. Let's say this is v1 and some angular speed, let's say omega. Okay, this is going to happen. Now find the velocity of center of mass of the system. So first part, a part, the velocity of center of mass. So the velocity of center of mass is not going to change because of this collision. Why? Because there is no any external force which is going to act here. So the velocity of center of mass initial and final will be same. So initially it was having its velocity as mv plus this mass has no velocity upon m plus m. So the velocity of center of mass initially before the collision and after the collision will be same, that is mv upon m plus m. Now let's go to part B. Find the velocity of particle with respect to center of mass before the collision. Okay, so the velocity of a small m with respect to center of mass is equal to velocity of a small m with respect to ground minus velocity of center of mass with respect to ground. So velocity of m is v, and this is center of mass has mv upon m plus capital M. So we'll have capital M into v upon small m plus capital M. So this is the velocity of a small mass or particle with respect to center of mass. Now asking C part, find the velocity of rod with respect to C before the collision. So velocity of rod, capital mass, with respect to center of mass before collision is equal to velocity of capital rod minus velocity of center of mass. So it was 0 and center of mass was the velocity of mv upon m plus m. So this is the velocity of rod with respect to center of mass before the collision. Now let's go to part D. Find the angular momentum of the particle and the rod about the center of mass before the collision. Okay, so angular momentum. So the angular momentum of particle and of rod. Okay, so the angular momentum of particle, let's say m with respect to center of mass, is equal to mass into velocity of m with respect to center of mass into the lever arm distance, that is x, perpendicular distance, that is this distance, because the center of mass is on this line and the particle is coming on this line, so this x distance. So what will be that x? So let us calculate first that x. So how do we get that x? So that x can be calculated here, like okay, so suppose this as the origin and this is so x coordinate of center of mass is x, and that is equal to this capital M into L by 2, because it is at L by 2 coordinate, plus a small m into 0 upon m plus m. So x is equal to ml by 2 a small m plus capital M. This is the value of x. Now substitute the value of x. So m, velocity of small m with respect to capital M, is mv upon m plus m. X is ml by 2 m plus m. So this will be m square vl upon 2 m plus m to the whole square. This is the angular momentum of particle with respect to center of mass before the collision. Now the angular momentum of rod with respect to center of mass before collision is equal to this m into velocity of m with respect to center of mass into lever arm distance. So this is center of mass, this is rod. So the velocity of rod with respect to center of mass is this. So it will be L by 2 minus x. Why? Because this is x and this is L by 2. So this will be L by 2 minus x. So this is m, and this value is how much is it? this is mv upon m plus m. So mv upon m plus m upon L by 2 minus x. So L by 2 minus ml upon 2 into m plus capital M. Then you'll get as mm square vl upon 2 into m plus m. So this is the angular momentum of body with respect to center of mass. Okay. Now let's go to E part. So E part, it is asking find the moment of inertia with respect to center of mass. Okay, so this is rod, this mass is lying here m, this is center of mass, and one mass is lying here m. So if this distance is x and this distance is L by 2 minus x. So I with respect to center of mass is equal to, this is center of mass of rod. So I of mass with respect to center of mass plus I of rod, that is capital mass with respect to center of mass. So this will be mx square plus, this can be written as ICM plus m L by 2 minus x whole square. This I have used here parallel axis theorem. So if you calculate this value, then you will have mx square plus ICM is m, this capital M into L square by 2L plus m L by 2 minus x to the whole square. If substituting the value of x, you will get as 4m plus capital M upon 2L a small m plus capital M into ml square. So this will be the moment of inertia with respect to center of mass. Now the last question, that is F part, it is asking find the velocity of the center of mass and the angular velocity of the system about the center of mass after the collision. So the velocity of center of mass will be same before and after the collision, that is mv upon m plus m. There is no change before or after collision because there is no any external force. But the angular momentum can be written as, suppose this is the mass which was having the velocity v before collision, and this is, suppose this is center of mass and this distance is x. After the collision, now it got stuck to it and center of mass has got the velocity with vcm and omega. Okay, so we'll apply the conservation of linear momentum, that is initial angular momentum and final angular momentum should be equal. So initial angular momentum is mv into m into v mv into x. This is initial angular momentum, and final angular momentum is I with respect to c into omega. So I we have calculated, x we are knowing. So the omega, if you do the calculation, I am not doing that, you will get as 6 mv upon 4m plus capital M into L. So this is the angular speed, angular velocity of the rod and all the system with respect to center of mass of the system.